Okay, this time this video will cover the divide and conquer strategy to solve problems in computer science. There are several problems in which this strategy has become successful and really very successful, like merge sort or counting inversions in a ranking or even um, in a sorting method like quicksort, the randomized quicksort, the median and selection, which are operations that are very common in the database development environment, and also geometrical problems just as the closest pair of points. So divide and conquer means that we divide a problem into two or three several subproblems of the same kind, but when we divide the problem, we reduce the complexity. We reduce generally the size of the input. And then we solve each of those subproblems recursively. And finally, we need to combine the solutions to subproblems into an overall solution. So these three things we need to keep in mind all the time, that these steps are sequential, are consecutive, and the first one is just dividing the problem into several subproblems. Now, this will be done recursively. So you divide a problem into several subproblems, and then the subproblems into several subproblems, and so on, until the problem becomes really easy or trivial to solve. Once you get to that point, we solve it, and then recursively return and combine the solutions of the problems of the subproblems into an overall solution. So the subproblems are, those solutions are found and combined to find the solution at the next level up until we get to the starting point and we solve the problem completely. The most common usage is just dividing the problem or the input size into two, so let's say into two subproblems of size n over 2. So we might have a problem that has, or for example, a sorting algorithm that has to sort a file with n entries and divides the file into two subfiles of size n over 2. Or we might imagine a problem, a geometrical problem, and then we divide, let's say, the number of points on the plane into the points into two subplanes of size n over 2, or the points are reduced by 2. And then we solve the two subproblems. Recursively means that the two subproblems are divided into two subproblems and two subproblems until we can solve them very easily, and then we combine the two solutions into an overall solution. This is, as you can see, generally dividing a problem into two subproblems in the long run takes about big O of n time, and combining the solution in its most common usage takes about big O of n time. But not all the time that needs to happen. We will get to that point in this part of the class. So remember that generally we have a brute force solution, which is theta of n squared. Like comparing, let's say, if we are sorting a file, the brute force solution would be just compare each element to every other element, and that takes obviously n squared. If we are trying to solve a problem, a geometrical problem, just like the closest pair of points, then we would also need to compare the distances between each possible pair of points, and that is again n squared. But if we apply this strategy, we will be able to achieve times like big O of n log n. Let's apply the idea to merge sort, which is a problem just to, I'm sure that all of you are familiar with a sorting algorithm, but to give you some context, let's define the problem. So we're usually given a list of n elements from a totally ordered universe, okay? And then we need to rearrange them in ascending order, like a group of songs. And we can sort them by name or by artist or by time or by album. And we can choose any combination of keys. Then obviously sorting algorithms have a lot of applications all over, but there are some really obvious, like organizing an MP3 library or displaying the results in Google's PageRank results, or list the RSS feed news items in reverse chronological order. Those are straightforward sorting applications, but some other problems are more subtle but still require sorting as the basic strategy to reach the final solution. One of them is identify the statistical outliers. Okay, so when we might be given a series of data, and we know that that data follows a pattern. It has a mean and well-known behavior, but some points might deviate very much from that average behavior, and those are called statistical outliers. And to be able to find them, we first need to sort the file or the database, all the data. Also, when we do binary search in a database, to be able to perform binary search successfully, we need the elements to be sorted before we even attempt it. Or when we remove duplicates in a mailing list, then also when we need, the easiest way to remove those duplicates is first to find them. And how do you find them? Well, by sorting the whole file. Then the duplicates you'll be bringing all the duplicates together, and then it's easy to select which ones you keep and which ones you don't. For the convex hull, another problem of the geometric nature, we were given a set of endpoints on the space, as I'm trying to depict here, and then we want to find the smallest set of points that contains all the points, and that smallest set is given by the convex hull, and the convex hull would be this one. In this place. So we have a convex polygon whose vertices are points that are originally part of the set S, and then have the property that any other point on the set is contained in that polygon. That's the convex hull. To solve that problem, we also need to first sort the points or the data. Also to find the closest pair of points to, this is not so obvious. We have seen that before. We visited the brute force solution. But what we will do is just begin dividing the plane into two parts, which separate the set of points in more or less equal parts, and we keep dividing and we keep dividing and we keep dividing, and then we do that recursively. When the problem becomes really easy, really trivial, we solve it, and then we combine the solutions from the solutions involved to get back to the next level above the recursion tree. Now okay. So another one is interval scheduling, interval partitioning, and minimum spanning trees like Kruskal's algorithm. We'll see that in a while. Now let's begin by focusing right now on merge sort. Merge sort is a very popular algorithm, and it is a great example of the divide and conquer strategy. And why is it so? Because we begin, let's say you have a file to sort, like the letters of the word algorithm. You want to reorder them in alphabetical order, ascending. So what we do is just we would divide the file in two parts. The one containing the first half of the word, Algor, and then the second one containing the second part of the word. And then we sort the left half, so we have AGLOR, and we sort the right half and have HIMST, and then we merge the results of these two already sorted files into a final file, a destination file. Now, how do we do that merging? Well, the merging is done by comparing elements of both files. In the beginning, we start with a pointer pointing to the first element of each file, and we simply compare the elements pointed to by these pointers, and we choose the smallest one, and the smallest one is the one that makes it to the final file, the destination file. So and then afterwards, after one element is being copied or passed or moved from any of these sorted lists into the final destination file, then we advance the index by one position, and we keep on doing it whenever it's necessary, whenever one element from one file goes to the final file. So in this case, we are pointing to AI in the left-hand side and to BJ in the right-hand side. And depending on the outcome of the result, either BJ or AI will come to the final destination. And when that happens, then the corresponding pointer is advanced one position. Then obviously we will get all the resulting file elements will be sorted just by the way in which we perform the merging part, because we are always selecting the smallest element to be consecutively added to the final destination file. Then this is the pseudo-code for the merge sort. That's the implementation. So we have the program, let's say, named merge-sort, taking an argument. The argument is a list of elements, let's say letters or files or records or something to be sorted. And then if the list has one element, we return the list. This is the stopping condition for the recursive process, because this is a recursive process. Why? Well, because we are calling it here again. So once we pass, if we pass this test, if we still have something to sort, I mean, if it has more than one element, then this statement will not be executed, and we get directly into dividing the list into two halves, A and B, and these two halves are submitted immediately to merge sort itself. So merge sort would be called again, but this time the input will be just the left-hand side of the file, of the original file, and so it is a simpler problem. And what will happen is that when the execution gets to this point, then the program begins right at the beginning again. And if that new argument has more than one element, this statement will be skipped, and then we will get to divide that left half into two halves, left and right. So now we have the left part of the left and right being fed into merge sort again, and we do that, and we do that, and we do that recursively until we find a list of one element, and then we never get to subdivide the file again. We just simply return that one element and pop out of the function to the next recursion level above. So now the level above will have a result on this part of their little subproblem, but still has to work on the right part of its little subproblem. So it would do it recursively again. So once we get to this call, this part would be subdivided, if it has more than one element, into two halves, A and B, and then this same process would start. And this generates a binary tree, the recursion call tree, we call that. And when we finally get to a point where we get an answer from merge sort A and an answer from merge sort in this second line, then we simply merge those two results into a longer list L, and we return L. By the way, remember that we are always using the same name A to store the sorted version of the same subproblem. So if you want to follow that or represent that as a binary tree, it would look like this. So let's say we begin with the word algorithm. Then, so we would divide that input into two parts, A and B. A would be algor, and B would be the word ITHM, the subproblem ITHM, and then so we would submit this to merge sort. That is, when we enter algorithm here and we divide it into two halves and pass the first half to the first recursive call. So then that means that the program would enter itself again, and then if it has a list larger than one element, it will go to divide the list into two halves. And then so this list would have two halves, let's say ALG and OR. In this case, we do not have an even number of elements in that file, but we have an odd number. But the division can be done in a way that the difference between those two halves is at most 1. So then we submit as the code says, the left part of the problem submitted to the algorithm. So we submit this ALG part, and we divide it again because we make this recursive call and enter, and now ALG has more than one element, so we divide it into two halves. Let's say these would be the two halves, and then we would pass the left hand part to the same program, and then we would get the a smaller problem. We divide, since this, when we execute that merge sort call again, the program would enter again, but this time we have a file of only two elements, still has more than one element, so we need to divide it into two halves. which would be A and L. And then we submit A again, the left-hand side part, to merge sort. And as we enter the program call again, we find that it has one element, so it returns that one element. We get A and pops out, goes away, execution is finished. No more calls are generated. I will indicate it with this grounding symbol. So that means that now the control of the problem goes to the next level up. So for this level up, we are done with the left-hand side part. So we go to the second line. We can get now, we return A in this case and store it in this variable. And then we go and merge sort the right part of the problem, which is just the letter L. And when we do that, so the next thing to be executed would be submitted to merge sort, but merge sort finds that it has only one element, so it returns it and exits. So we return the L and exit. And where are these? Now, when that happens, we are at this point of the problem. At this point, when we returned from the two recursive calls. And now it's time to merge. So we merge A and B according to the process we described before. And we get, now since A is smaller than L, I will get that in a different color. Then we would return, what we would return would be, again, A and L. In red, I am writing the sorted version. Since AL was already sorted, well, that's what we would return. And this would be the first part, the first call of the next recursive level when we submitted ALG to merge sort. So we are done with the left-hand side part. Now we need to process the right-hand side part, and that has the letter G. So we continue here with G, and what will happen? Well, G, as we say, merge sort of G is only one element. The call would be made, and here this test would find that it has only one element, so it returns that element and pops out. This is not executed, we just exit from the function with nothing, exit from the function downright. But we would return, but notice that then when it returns at this point, what we get is we return the same element, we return G, and it is already sorted because it's only one element. So when we go to the merging step, we can go to this step because we are already back from the two recursive calls. So we have the results for the left part and the right part, like here, and we're ready to merge. And when merging them, then we would have something like, well, we would begin by comparing A against G, which is smaller. Well, A is smaller. Then we compare now L against G, which is smaller. G is smaller, so G goes there, and then L would follow, and that's the end of the merging process, and we're done with this part. So this means that we pop from here, from this level, we return the sorted version, this is it, and we are ready now with the left-hand side part of the above level of recursion. For corresponding to this bigger problem, ALGOR. So we would, in that recursive level, we would be done with the first recursive call, which is returned from that recursive call, and the result was AGL. And now we would submit the right part of the file to merge sort again. So this would mean that now OR is submitted to merge sort, and when we submit that input, then we would get the we would enter here with OR. It has more than one element, so we need to divide it into two elements, O and R, and you can guess what will happen. So we will first we will enter the left-hand side part of the problem, and the merge sort would find that it has only one element, so it returns it back and exits. So, yeah, that means without doing any more recursive calls, and returns something which is O. Or maybe I should have painted it in blue. Okay, and then when we do this, we are back to this recursive level, and we would be done with the first part of with the first recursive call. So we proceed to the second recursive call, the one containing R. So you can see that when we submit that single element, this condition will become true. It has only one element, so it would return that one element and exit without further ado. And then we have a merging process here, because we reached the point right after the two recursive calls, so we're ready to merge. And when we do the merging, we would get O and R, just because O precedes R. And then what happens? We would be here, we just return that, L would be OR, and as we exit from the second branch of this tree, then we go to the next level above. We're here. And the next level above, we already have the result from the first part and the result from the second part, and we are ready to merge. So we need to merge A and B, and we would get, so we would compare, as you see, first A against O. A comes first, then G against O. G comes first. L against O. Well, L comes first, and then O and R. That's what we would get back from the merging process. And then, oh, lo and behold, we are just at the end. We just finished the first recursive call of this recursion level, which was the original one, the start one. So once we were done with that, we would be in this stage. We just finished the first recursive call. So we go to the second one. In this time, we would submit the second file or subfile, ithm, and as when we do that, the first thing that happens is that, since we have more than one element, then we go and divide the list into two halves. in these two halves, then we would feed the left-hand side, the left-hand part first to the algorithm again. So we would have another call to merge sort with this file int, and so we would enter the program again with an input of 2 elements. So that's 2 is more than 1. So we divide the list into 2 halves. In this case, int, and we submit I. And you can see that after we submit I, that's what we would return, because it's a single element. So we would return I here, and the left part is already done. So now we need to go and do the second recursive call at this level. We would be submitting T only, and that would mean that we return only a T, the letter T, and then we would have int here, and then we would be at this point of the problem, of the subproblem IT. So now we need to merge the 2 elements, and int, when merged, we would get it back because I precedes t. And then we would pop up and go to this other level and find that we are already done with the first call of this level. So we need to go to the second call. So let's go get it. The second call has h and m, and then it would be divided, and then h would be submitted, and then from that we would return only h, and we are done with the first part of the problem. We go and do the second part of the problem, which is the single letter M. Single letter M. So let's get this tool. And we would have M. And as you can guess, it will return as soon as it M back and exit. And then we would reach the point right after the 2 recursive calls. So we are ready to merge, and we merge H and M. And since H occurs before M, that's what we would return, the H and M. And at this point, we are done with the 2 recursive calls from this level, from this subproblem, and we are ready to merge them. So we will have to merge this. So we return the merge of the files IT and HM, and we do that according to the merging process we already know. So compare I against H, we would get I, then I and T against H, then H would come first, then T against M, then M would come first, and then T would come afterwards. And by that time, we are at the end of the second recursive call of the first recursion level, the top one, and we need to merge the 2 results that we get from the previous recursive calls. So then we get to merge AGLOR with IH and T, and the result would be, well, first compare A against I. Well, A makes it to the final file. Then advance the pointer and compare G against I. Well, G comes first. Then we advance the pointer then we would be comparing L against I. So I comes first, and then we would be comparing now L against M. L against M, so L goes here, and the pointer would be advanced to O. Then we'll be comparing O against M, so M makes it to the final destination, and then O against T, and O makes it to the final destination. And then we will be comparing R against T. R goes first, and then T. And then this is what we would get, the final version sorted file. And after following the code or the recursive call tree for merge sort. Now, whenever we analyze this kind of algorithm, we can always write a recurrence relation. We can always write the time or the maximum number of compares that comparisons are the significant operations in this problem. So we just need to count the number of compares. Let's say T of n is the maximum number of compares to merge a list of length n. Okay? So because of what we just saw, we can say that the time that taken to, or the number of compares taken to sort an entry of size n is the same thing as the time dedicated to the first part plus the time dedicated to the second part plus the time required by the merging process. And remember that merging these two files of size n over 2 would get us a file of size n, and that since each of those elements are passed to the final destination only after a comparison is made, we conclude easily that we have made n compares. So this is a complete recursive problem, a recurrence relation for this recursive problem. So we have, in the case that n is 1, so the input is already sorted, that would be 0. That's the smallest meaningful case is n equal to 1. Then that would require 0 effort to sort because it's already sorted. But anything bigger than that, for n greater than 1, it would be represented by this formula. Just the time for the first recursive call plus the time for the second part of the file plus the merging of the two results from the recursive calls. Turns out that this quantity is really big O of n log 2 of n. And there's two ways in which we can solve this recurrence. Okay. So one is just imagine that n is a power of 2. So if that happens, if n is a power of 2, then we can easily divide it into two parts, and those two parts will be divisible by 2, and then all further subdivisions will always be divisible by 2, except the last step when we reach the size of 1. So then we would have a tree very similar to the one we saw for the recursive calls. And we would have, for example, so this problem, t of size n, the number of compares, let's take a look at this recurrence, will be composed by the time dedicated to the first half plus the time dedicated to the second half, or 2 times n over 2 plus n, the time required for the merge part. So here, dividing the file and submitting it to recursively to the same function really doesn't even need to be counted. It's just constant time. but merging the when we come back from the recursion, only until we come back from all the recursion steps, then we would have something to merge. And after we merge that, we would be doing n compares. So this is the significant amount of work done at this level 0. Then at the next level, in each of these levels, each of these parts of the same level has n over 2 elements, and we know that we need to merge the results from this recursive call plus the results from this other recursive call of this size into a file of size n over 2. That would take a time of n over 2. And what is the time required for the other part? Will also require n over 2. So we have now 2 times n over 2, we get n. Then in this case, the final two files, the final file would be a file of size n over 4, which results from merging two subfiles of size n over 8, and that requires just n over 4 time. N over 4 compares. And the same happens here, and here, here, and here. So the total number of compares is 4 times n over 4, which is still n. And that will continue happening for each of the levels until the last level. Then how many levels do we have in a binary tree? Well, that's log 2 of n. And each of those levels is adding n compares, so the total number of compares would be n times log 2 of n. When another way to see that algebraically, or to prove it algebraically, would be a proof by induction. Now, proofs by induction, in this case, what are we trying to prove? Well, the proof is that this closed formula, we call this a closed form formula, gives the same answer as a recurrence. And how do we prove that? Well, we found that the result from an empirical argument. This is the empirical argument, and an inspection, an observation, but we still need to prove it. And to get it really nailed down, we would do that by induction. So as you know, the first step in an induction proof would be, we'll test the base case, the smallest meaningful case, and see if the formula gives you the same result as the recurrence. So the recurrence would return, the smallest meaningful case is when n equal to 1. Then the recurrence would return obviously 0. And that's what we get from the recurrence. But what do we get from plugging in 1 in, you just evaluate t of 1. T of 1 would be 1 times logarithm 2 of 1. And it turns out that the logarithm base 2 of 1 is 0, and logarithm of any base, logarithm of 1, will always be 0, so this will end up being 0. So in other words, the number or the result from the closed form formula is just the same as the result that we get from the recurrence. So the base case is proved. Both, what we mean by the base case is that, yeah, those two formulas coincide in the simplest of all cases. Then we go to the inductive hypothesis, inductive step. To do the inductive step, we need to suppose that this property, both formulas are equal for a given size. Then they will be equal for a bigger size. In this case, let me write the inductive hypothesis really, or the inductive step is really trying to show the following. Let's say we want to show that T of n, the recurrence, and close equal to the closed formula for n, then they would be equal, then T of 2n would be equal to what the closed formula says for 2n, for an argument of 2n. And as you can see, this is the inductive hypothesis. And to prove that the conditional statement is true, we need to prove that the conclusion actually follows from the antecedent. Okay, so the consequent is follows the antecedent. So we suppose just that T of n is both formulas give the same result for n, and then we try to prove that the same result would follow for a bigger number. In this case, it's not the next one. This is not the ordinary recursion proof that you see, but we would be recurring on multiples of n. So the next multiple will be 2n. So let's see. This is the goal. If we can show that this happens, that the recurrence is giving us the same answer as the formula, then this whole conditional will be proved, and that is and if you put together this with the base case, then you can see that it will be valid for any number, because since you can reach any, you can suppose that you can get to any place, because you can get to the first step, and you have proven that if you're in a given step, you can go to one step above. Then that means that in the end you will be able to climb the whole stair, like in the example of we made in the beginning. So let's try to do that. How do we do that? Well, first we write the recurrence. We start from the recurrence. T of 2n equals 2 times T of n plus n. And then since we can apply the inductive hypothesis, we just assume that they give the same result for a value of n. So then we just plug, instead of T of n, we can plug in, let's again, I will encircle the inductive hypothesis in green. This is the inductive hypothesis, and this is what I will apply here. So T of n can be substituted by n log 2 of n, because I just need to assume that that's inductive hypothesis, and I need to get to my goal. Let's see if we get there. Okay, so we have 2n log 2n plus 2n. Factor these 2n terms out, and you get this parenthesis. Okay, so so you would get 2n, and then inside you would get the well, at this point it's easy to see the step from 2n log 2 of n plus 2n. So we just factor 2 of n out, and we would get log 2 of n, and we would get plus 1. Okay, and now log 2 of n is just the, remember that, let's rewrite it here. Log 2 of n is just log 2 of 2n divided by 2, which by the laws of the logarithms turns out to be log 2 of 2n minus log 2 of 2, and this is equal to log 2 of 2n minus 1. Okay, so this we can write log 2 of n as log 2 of 2n minus 1. So this is what we would be doing here. Just write log 2 of n as log 2 of 2n minus 1, plus this 2n keeps the same. And then we cancel these terms, this 2n with this negative 2n, and we are left with 2n log 2 of 2n. So that it turns out that we could reach this point, which is the result from plugging in 2n to the closed form formula, and we started from the recurrence. So indeed, if we assume that the inductive hypothesis is true, then we would have that this result would follow, and this, when considered together with the base case, would complete the proof that the closed formula gives the same result as the recurrent formula. So that is the number of compares taken by merge sort is n/2. Now, it turns out that we not always have an input of size a power of 2. So what do we do in that case? Well, as you saw, we have to divide the file in two parts as equal as possible and similar as possible, and that would be, one of them would be the floor of n/2 and the other one would be the ceiling of n/2. So we would have this formula, okay? T of n is equal to the time taken by the left-hand part and by the right-hand part. In this case, the right-hand problem can conceivably be bigger than the first one by 1. And then the work required to merge would be n-1, because we are always left, the number of compares required to merge those unequal files would be n-1, because we are comparing n-1 elements from the shorter file with n-1 elements of the longer file, and the other extra element would get into the destination file with no comparison at all. So now, what is the exact solution of the following recurrence? What would you say? We are looking for the exact solution. Is it A, which is n floor of log 2 of n, or is it the ceiling, or is it C, or is it D, or not even Donald Knuth knows? Well, Donald Knuth was the father of the analysis of algorithms, and he probably was the originator of all these proofs and observations. So it turns out that if you search in the literature, you will see that the right answer would be this one. There's no such exact solution. So what we look is just in the number of compares bounded by a function which is not too complex. In this case would be n times the ceiling of log 2 of n. Okay, so how would we go to do that? Well, the recurrence would be written in a similar way, only we have to change the less than or equal, smaller than or equal. And the n minus 1 from the previous formula, this one, can be substituted by n with no effect on the direction of this sign. So the right hand side will still be bigger than the left hand side. And again, we now try to show that the closed formula and the recurrent formula will give us the same result. And we proceed with the proving by induction as follows. So it's obvious that the base case holds because when n equals to 1, we have again the logarithm base 2 of 1 be 0, and making both equal to 0. But what happens if we have a number that is not necessarily an even number? Then let's define n1, n sub 1 as the floor of n over 2 and n sub 2 as the floor of n over 2, as the ceiling of n over 2. And note that when we add those two numbers, n1, n sub 1 plus n sub 2, we get back to n. For the induction step, we assume that the proposition that the claim is true for the numbers 1, 2, 3 up to n minus 1. What is a claim again? Well, that this inequality using this closed form formula is the same inequality as this one. Both inequalities hold. The recurrence and the n times the ceiling log 2 of n for closed form formula. Okay, so begin by assuming that it is the same, that it is true for the numbers 1 up to n minus 1, and we start from the recurrence again. So in this case, we get here t of n, we can write it as t of n sub 1 plus t of n sub 2 plus n. Now, when we substitute the inductive hypothesis here, because n sub 1 and n sub 2 are smaller than n, they fall into this range, then we can substitute the t of n sub 1 by what the closed formula says, like was here for n sub 2, and this will remain the same. Now we'll make a little change. We now write n2 instead of n1, but if you notice, n2 will always be bigger or greater than or equal than the floor of n over 2, than n1. So we are basically substituting this term by an even bigger term, so the inequality is not affected, but the expression is really simplified because now we are able to factor this term, the ceiling term, and we would get a log 2n of n2 multiplying n1 plus n2, which we know is equal to n. That would give us this part, and this n would give us this other part. Now we can again make a similar argument as the one we made in the previous case or the previous proof, and let's write n sub 2 as the ceiling of n over 2. Then n over 2 can be written as 2 to the logarithm of n, 2 to the logarithm base 2 of n, the ceiling, over 2. This number can potentially be bigger than this other one because we are raising 2 not to the exact logarithm of 2 of n, in which case we would get only n, but we're raising it to power which is higher, potentially higher, because it could be the ceiling. So this symbol is justified, and then since then we can, by the laws of the algebra of the ceilings, we can just eliminate the ceiling and get and write it as 2 to the ceiling of n base 2 of n over 2. And if we take now logarithms in both sides, because we want the logarithm base 2 of n, the ceiling of the logarithm base 2 of n, then we would get the logarithm base 2 of n2 in this side, and here we would get, when taking logarithms, the logarithm of 2 to the ceiling is just the ceiling, and the logarithm of 2 as a divisor, the base 2 of 2 is 1, and since it is in the divisor, it would be subtracted by the loss of the logarithm, and we would get this expression for log 2 of n2. So we substitute log 2, the ceiling of, log 2 of n2 by the ceiling minus 1, and we keep the rest equal. And since this number can be potentially higher, then this equality turns into an inequality, but in the same sense as the previous inequality. So this number is bigger than the original one, and we can simplify this term when developing the parentheses and canceling this negative n with this positive n. We would get n times the ceiling of log 2 of n. Therefore, this inequality would hold, and is the same thing as what is told by the recurrence relation, even if it's an inequality too. So therefore, this fact that we guessed from the recursion tree is really sound and true, and will remain true because we have already proved it. Now, you might ask yourselves, well, is there a lower bound for all the conceivable algorithms, not only those based on comparisons? Well, we can answer that question with having comparison trees as a model of computation, and in which we can access the elements only through pairwise comparisons, and all other operations like control, data movement, etc. are free. Suppose that the only cost comes from comparisons. So really the cost model would be the number of compares. Is that realistic? And the answer, yes for Java, Python, C++, or yes for merge sort, insertion sort, quicksort, heap sort, or no, like in bucket sorts, radix sorts, and so on. So this is true, and also this is true, because all these are comparison-based sorts. But radix sorts and bucket sort, they are not based on comparisons. They are based on the properties of the keys. They have to operate on the right keys, and the keys need to be numerical in some nature, so that and in that case, not only numerical but expressible as in as a number in some base system. For example, base 10 or base 2, base 3, whatever the base. But then so they do not obey, they sort the elements with no comparisons at all, and at the cost of perhaps a suboptimal use of memory. But that's everything that the worst that can happen for this kind of sorts. And they are considered special case because not all keys are expressible or are able to be expressed as a number in a number system. So just keep in mind that for some special cases you might have these two kinds of sorts, or even with variants or some other variations that can be better or would give a better performance than comparison-based sorts. Then this is a comparison tree. So we can reach each of the possible permutations of, let's say we have only 3 keys, we can reach any of the possible permutations by a path in this tree. And we see that the height of the pruned tree is just the worst case for the number of compares. So what is the maximum number of compares required to get to the farthest away elements in this tree? Of course, it's related to the logarithm because we were looking at a binary tree because we are comparing one thing against another. So we can think of a lower bound for the sorting problem because what we got before was an upper bound. But is there a lower bound? And it comes from arguments in information theory, and we can assume that an array, the array that we need to sort, has n distinct values, so they do not repeat. And in the worst case, the number of compares equals the height h of a pruned comparison tree. So we would have a comparison tree like this one, and it has been pruned because we do not have any redundant branch. We can do more compares than we need, and in such a tree the number of compares is equals to the height of such a tree. But for a binary tree of height h, this tree would have 2 to the h leaves and n factorial different orderings would imply n factorial reachable leaves, just as we saw in this case. The 3 factorial permutations, there are 3 factorial permutations of 3 elements, and that's 6, so we have only 6 leaves in that tree, reachable leaves. So in general, we would say that the lower bound for the sorting problem would be for any deterministic compare-based sorting. Deterministic because as you can imagine, there are some probabilistic approaches or stochastic approaches, but deterministic compare-based sorting algorithms must make big omega of n log n compares in the worst case. And the proof is not hard to follow, but we do need to know a little bit more of combinatorics and because we are applying Stirling's formula. So if you're curious, just take a look at this development and go and consult Stirling's formula for the factorial and substitute. Stirling's formula is an estimation of the factorial based on the exponential function, and it is like a shortcut. It is considerably less complex than the factorial function, and it grows more or less the same. So now let's say we have the following problem, but I will just stop now because we have seen already the divide and conquer approach as applied and as seen and illustrated with the merge sort algorithm. And we will see these other kind of algorithms later on. Thank you.